Okay, so we started talking last time about modeling with quadratic functions. And basically what we're looking for is when we have a bunch of data points, can we come up with a quadratic function that basically looks the same as the data points? And there are ways to do that. We're going to talk about that today. And one of them is called a quadratic regression. And this is something that we would just look up online nowadays. You know, they have quadratic regression calculators online. And I'm not even going to bore you with the details of how to do this to actually calculate it by hand, because we don't have to do that kind of stuff anymore. All right, so let's pick up where we left off. All right, this says make a scatter plot of the data and graph the function on the same coordinate grid. That sounds like a job for Desmos. It says calculate the residuals and make a residual plot. It says describe the fit of the function of the data. Well, we're not going to actually make the plot, but we can talk about what a residual is. So a residual is basically the difference between the actual value, which these would be the actual values here, and the predicted value, which this is going to be what we're going to use for the predicted value. So how close is this thing? That's what they're really talking about when they're talking about residuals. Okay. And what they're looking for in a situation like this is when a point isn't directly on this curve right here, what they're looking for is how close are we, number one, and number two, is there some points that are like above the curve and some points that are below the curve? Because then they kind of average out. You know, if they're all above the curve, then our graph would have to be something like pushed up a little higher. So like if all these points were above this graph, if we had to push it up higher, we might change this number from 1 to maybe 2 and push the whole U shape up. Okay, so that's what they're saying. So if there's numbers above and below, then it's like it's going kind of through the middle. It's going to be a pretty good estimation of what they're looking for. And they actually do this kind of stuff again in like business, like sales projections and things like that. So they do a lot of this kind of stuff. Also like cost analysis, you know, like what's the maximum number of items we can make from this amount of product and that kind of thing. So it's there is a lot of application for this kind of stuff. It may not seem like it, but there really is. All right, so on that note, let's go ahead and call it Des. And there's that. All right. So let me get this stuff written down before I move Desmos in here so that we can look at the points. One moment, please. Okay. So here comes Desmos. Okay, so first thing I'm going to do is go ahead and plot some of these points. And first one is going to be, we have to make this a little smaller actually. Yeah, I didn't want to move over though. Let's leave them here. Okay. So then we're just going to plot some points. $13. There's that guy. And yeah, we're probably going to label these things. That would be good. So we got 213. We got 8. And we have 0, 6. We're going to have 1, 9. And finally, we've got 212. 12. Let's go ahead and label those guys. There we go. Okay, so it kind of looks like it might have a U shape, right? So then the next part is we're going to go ahead and plot this graph. So we're going to have 2x squared. Okay. So 2x squared, the minus x. Okay. So there we go. So what do you guys think? Is this a pretty good estimation of these? No, I don't think so either. So what they're saying when they say about residuals is, like, for example, here, this guy is at, where's my cursor? There we go. He's at 0.6, right? The closest we get to that is about, what's this, like -1.6. So he's like 1 off. And then this guy over here is about 1 off. This one's a little more than 1 off. These guys are pretty close. But yeah, for the most part, I'd say it's pretty well off. What I would think might work is maybe if we move this guy over 1. And the way we do that, so we want to go back 1, we do here, we go parenthesis. And then we need another parenthesis over here. Then we go, by moving back 1, let's say we'll make that x plus 1, right? It does the opposite. What do you think about that? That's pretty good, isn't it? So what we were noticing from the residuals was that they looked like they were about 1 unit off. Everybody, and most of them were on the inside of the U shape. They weren't really on the outside. So here we've got one that's right on. We've got a couple to the left of it. We got a couple to the right of it. So that's probably a pretty good estimation. Okay. So see, that's the kind of thing they'd be looking for, and this is what they would do to figure out the data points. All right. So with our adjustment, I think we hit it pretty good. All right, so that's basically what they're looking for. So let's make sure we covered everything here. We drop down des for a second. All right, so we did our scatter plot. So I plotted these points on Desmos. Then I took this guy here, put him up, and then we decided that it wasn't really a good fit because most of them were like a unit too small. So we moved our graph 1 unit to the left and it looked pretty good. Okay, so initially we thought the fit was not so great. Okay, so see how that kind of stuff works? And like I said, there's a way to calculate that stuff, and we'll be doing that here in a second. All right, so let's continue on. All right, so this is the same kind of thing, so we're going to make another scatter plot. So this is pretty much second verse, same as the first. All right, so let me get this stuff written down real quick. And we'll get going. All right, so we got minus x squared plus 3x plus 2, minus 2, minus 6, minus 1, minus 1, 0 and 3, 1 and 4, 2 and 3. Okay, got it. All right, let's bring Desmos back in. There we go. All right, so let's go ahead and do our new one here. So this one's going to be minus 2, 22, just minus 2. It's 6. Then we've got minus 1, minus 1. So minus 1, minus 1 there. Hold on. Minus 1 there. 0, 3 this time. Let's change him to a 3. Then change him to a 3. There we go. 1, 4. Let's make this guy a 4. And this guy is 2, 3. So there's our new guys. Oh, yeah, I messed this one up. Hang on. As I say, one guy's out of whack, but I realize why. He's -6, not 6. That's more like it. Well, that one looks pretty good as far as looking like a parabola. All right, so let's bring in the new guy. That was not good. That's better. Still missing the 2, 3 though. Huh. Okay. 1, 4, and then we got 2. Now we're back in biz. All right, so let's go to this guy. So he's going to be -x squared. Okay. And then plus 3x. And then plus 2. So let me see. All right, what do we think of this guy? So we can see him a little better. Yeah, that one's pretty good. Because look, we've got 3 of them that are actually touching out of the 5. This one's real close, and this one's only a little bit off, and this one's outside, and this one's inside. So yeah, that's a pretty good estimation. And the point of the estimation is that if we want to know some points over here, we want to get an idea, like we said, okay, well, what if we're down here at 5? So we're at 5, we'd be down here at -7. Okay? So that gives you a possibility to get some other approximate values. So yeah, that one looks pretty good. Wouldn't really change much there. Cool. So you see how this stuff works, but again, Desmos is the guy we want here. So again, the residuals, like I said, these guys are pretty much right on point, right? You know, this guy would be something very insignificant, less than 1. This one is even closer. This one would also be less than 1. This one's probably right on the money. And this one here is less than 1 as well. So they're all less than 1 away. And we got 1 above and 1 below. So that's a pretty good curve. We can live with that one. Questions? All right. So let's see what they got now. Drop him down. So yeah, we feel pretty good about that one. What do we got here? It says use a graphing calculator to find the quadratic regression. Yeah, we're going to use the internet. Because quite frankly, graphing calculators, the graphics are terrible. And it's probably easier just to use something online. Okay? So what you're going to do is we're going to go ahead and plot these points again. I'll just take a picture of it this time. And we'll put it into this quadratic regression thing. And like I say, I'll pull one of those up online here. And I think I may have put a link in the modules to a quadratic regression calculator that you can just grab it there. Let's go ahead and get this real quick. All right. So let me pull one of those guys up. All right, so let's bring this guy in. Quadratic regression calculator. There we go. All right. Easy calculation. That sounds like a good one for us. Okay, so this says enter the x values and enter the y values. Okay. So our x values for this first guy. Of course, my phone shut off. It's just 0, 1, 2, 3, 4. Okay. 0, comma 1, comma 2, comma 3, comma. Enter the y values. These are going to take a little longer. So this is 15.5. Hang on. 15.5. We've got 11.21. Got 8.43. We've got 5.67. And then finally we have 3.43. Okay, so you just put all the points in. All the x's are here, all the y's are here. You hit calculate and check it out. So here is our actual equation. So it's going to be 0.094 x squared minus 4.145x and then plus 15.373. So what this has done is this has calculated a quadratic that fits our data the best. And there it is right there. So if you want to check that, and you said, okay, I've got a point here at 1 and it's 11.21. So where's, okay, so 0 starts here, right? And 0 we said was 15.5, right? Yeah. So you can see that guy there, pretty much at 15.5. Then we move over to 1, and we're going to be at, I think it was 11.43. Hold on. It'd be nice if I could get this all on the screen at the same time. But I don't think it's going to happen. That's pretty good there. So here's 0 at 15.5. Then we go to 1. We got 11.21. So 1 is over here. So 11.21's down here. So it looks like that one's a little bit off. But again, it won't be perfect either, but it'll be pretty close. Okay. So basically, like I said, find one of these guys. You saw how quick I just grabbed one online, right? And it gives you that. Okay. So then they got a second one here. All right. So this guy here, the new guy, put in our x values. Some of them they'll put them in as pairs, but this one's just putting all the x's together, which is fine. So 100, 500, 900, 1500, and 1700. There's those guys. Notice how the thing's calculating as we go. And then the bottom guys here. And the .2, and then 362.3, 312.2, and then 307. No, much difference, but there. Okay, and then calculate. So here's our new guy. So notice that as our x values went up, our y values were going down. So this time we've got an upside down parabola, right? You see that's what we got going on here, right? Well, that's interesting. We got a little U-shaped thing going on here, right? So we're going down, but they figure at some point it's going to start coming back up, which is interesting. Okay, so basically, like I said, you just look one of these guys up, you plug in your numbers, and it'll give you a quadratic equation that best fits what we got going on here. Okay, questions? Yeah, so this is pretty cool stuff. I mean, you just, like I say, you just grab some stuff off of Google and we're all good to go. And if you pick a regression calculator and you don't like the way it runs, or it's hard to put the data in or something like this, find another one. I picked this one because it had the word easy in the title. That's why I picked this one. All right. Okay, so that's what's going on with these guys. So again, you see a lot of this stuff is technology based, which is cool. All right. Let's go ahead and this is like a EOC kind of question. So it says the function, remember that the minus t squared, the minus 16t squared, this is pretty much the force of gravity in any of these problems. So that's what this is. This is the force of gravity right there. And then the 96t is like an initial velocity, like if a guy's kicking the ball, this is how much leg he puts into the ball, okay? And then the last one is the starting height of whatever we're talking about. So this one's going to start 10 feet off the ground. All right, so let's look at what they say here. It says select all true statements. It says the initial height of the projectile is 10 feet because h of 0 equals 10. That's true, because if you plug in 0 for t here and here, right, the minus 16t squared is going to go away, the 96t is going to go away, you're left just with the 10. So this guy's cool. Check. All right, the next one says the initial height of the projectile is 90 feet because h sub 0 equals 90. And I don't even know where they got 90 from here on this thing. So that's not it. So next one says the projectile reaches its maximum height at time equals 3 seconds. Well, we're not really sure, are we? So remember, this is that whole bit minus b over 2a, right? So here is our b value, right? So minus 96. Let's see, my pen is going to be weird today. And then over 2 times negative 16. Okay, so that'll be negative 96 over negative 32. So we'll break out our calculator here. Let's bring him into the scene. There he is. So the negatives are going to be positives, right? And two negatives will cancel out, give you a positive. So you can just do 96 divided by 32 is in fact 3. So yeah, we feel good about that one. Check. Next one. It says the projectile reaches its maximum height at time equals 6 seconds. No, we just figured out it was 3. So don't have to worry about that. It says the maximum height of the projectile is at h of 3. Yes, because remember what we've done here is we figured out we're going to have a parabola that's upside down, right? Because we have negative out in front of the t squared. We just figured out that this point here is going to be the x value of the vertex, right? That's going to be a maximum point. Okay. So if we plug 3 back in for t up here, so if we plug a 3 in here and another 3 in here, that will give us a value for the maximum height. Okay. They're not asking us to actually calculate it. We could, but we don't have to. But we know that the maximum height is going to be at the time t equals 3. So check. So every other one of these worked. Questions on that one? Okay. So let's go ahead and check out an ACT/SAT question. All right, so this is a basketball is thrown straight up in the air from a height of 2.1 feet with a velocity of 7 feet per second. It says which function models the height of the ball after t seconds. So which one of these guys, which equation will we use here? Oh, by the way, Chloe, I saw your note. Just send me a reminder, like maybe Wednesday. All right, so what do we think here? It says our initial height is 2.1. Right? So remember we said that the initial height is just a regular number. So if we need just a regular number of 2.1, which one of these are not right then? Which ones can we eliminate right now? Which equations don't have a plain number of 2.1? So C doesn't, right? He has -7. How about A? A has a 7 here. Is that good? Nope. This guy also has a 7. Nope. So right away, we're down to just these two answers, right? Okay, so notice these guys are all the same. Again, this is the force of gravity. This is our initial velocity, and this is our starting point. So we know our starting point is 2.1, so we got to be D or E, right? Okay, so one of them has +7, one has -7. So should we use D or E? Yeah, we're going to go with D. Good. So see how we figured that out? We just said, okay, well, we got our initial velocity, so that goes with the t, so that was +7t. And then the other one was a height of 2.1, so that's +2.1. That's the only one that fits the bill. Good. All right, and that happy note, that closes out 8.4. Got a couple minutes. Let's talk about 8.5 just a little bit. We'll do just a little intro on that one, and then we'll really hit that up next time. So we'll pop that up here real quick. Okay. So section 8.5, it says linear, exponential, and quadratic models. So this is where we kind of put it all together. And they give us some data points. And we say, all right, could I best represent these data points with a straight line? Could I represent them best with an exponential function or a quadratic function? And there's ways for us to be able to tell this. So we'll talk about the ways for a second here, and then we will, like I said, we'll get into this a little more next time. This is just a quick intro before we head out here. All right. So it says, determine whether a linear, quadratic, or exponential function is the best model for the data in each table. All right, here's how we do this. If it's a linear function, okay, the difference between the y values will be the same. Okay? So let's look at the y values. If I go from 1 to 3, I'm going to need some of the rights here. That would be good. So 1 to 3, that's going to be 2, right? If I go from 3 to 9, that's going to be 6. If I go from 9 to 27, that's going to be 18. And if I go from 27 to 81, I'm not even sure what that is. Hang on. So 81 minus 27 is 54. Well, these certainly are not the same numbers, are they? So if the first difference is, if we kept getting like, 2, 2, 2, 2, then a linear function would work. But this definitely is not a linear function, so we'll cross him off. Okay? So then we take these guys and we do what's known as the second differences. So this is the first differences. If the second differences line up, then we have a quadratic. So what that means is we take these guys, I go from 2 to 6, that's 4. I go from 6 to 18, that's 12. I go from 18 to 54, that's 44, 34, 36. All right, so these are the second differences. And notice these guys are not the same either, are they? So that means this is not a quadratic. So by process of elimination, we've got an exponential here. But here's how they figure out the exponentials. Is you take the y value and divide it by the x value and see what you get. Okay? So you want to see, do I keep multiplying by the same thing over and over? So let's try that. All right, so this would be, we want to see what the ratios are. All right, if I go from 1 to 3, that's 1 times 3, right? So our ratio is 3. If I take 3 and multiply by 3, I get 9. So that works. And then 3 times 9 is 27. 27 times 3 is 81. So notice these ratios are all the same. We keep multiplying by the same number over and over, which is the definition of an exponential. Okay? So that's how that works. So you look at the first differences, if they're all the same, that's linear. If the second differences are all the same, that's quadratic. If you keep multiplying by the same number over and over, as we did here. So I mean, you can look at this and say, yeah, you do 3 divided by 1 is 3, 9 divided by 3 is 3, 27 divided by 9 is 3, and 81 divided by 27 is 3. So that one turned out to be exponential. And like I said, we'll practice this a lot more next time as well. All right. Let's maybe do one more of these and we'll call it. All right, so same deal. So like I said, you don't have to be real, specific about this. If you look at this guy, it's definitely not going up the same amount every time, right? So linear's out. And let's see, so if we do 2 divided by 1, that's 2, but if I do 7 divided by 2, that's 3.5. So exponential's out. So it must be quadratic, but here's how you figure this out. So we said, okay, so the difference here is 1. The difference here is 5. The difference here is 9. And the difference here is 13. Now, that's your first differences. Your second difference is if I go from 1 to 5, that's 4. If I go from 5 to 9, that's 4. If I go from 9 to 13, that's 4. So your second differences are all the same, which means we've got a quadratic here. So that's how that works. And like I said, we'll practice some of this stuff next time. I just wanted to give you an intro on that one. All right. Well, if you don't have any questions, I've already got attendance for you. So I will let you guys go. and we'll do it all again tomorrow.